I'm sorry that it suddenly, the Zoom conference suddenly crashed. I don't know why. I tested yesterday, it works really well. Let's wait for 2 to 3 minutes to allow everybody to rejoin.
I'm guessing you might not have a key because it said it was a free meeting.
We haven't passed the 40 minutes. Oh, I'm sorry. Oh, I'll figure out the key problem if it is the problem. But if I cannot figure out, maybe we can have a break every 40 minutes, right?
That works too.
Because yesterday I tried to do a Zoom conference over 40 minutes. It is working well. It's really bad. It sounded crashed and also destroyed our recordings. I can only record the remaining half of the lecture. Yeah, let me send another announcement. Oh, probably it's because of the 40 minutes long, because we started around like 20 and it crashed at 1:03. Yeah, it's about 40 minutes long. Okay. Okay. Okay, looks like everybody is back. Hello? Can you hear me?
Yeah, we can hear you.
Okay, great. So let us continue. Really sorry about that. I need to figure out the key issue. Okay. Yeah, let us continue with this. Wait a second, I need to make sure it is recording. Okay. 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 So so now we can see for arbitrary general constraint optimization problem, we can convert it into minimax optimization problem on its Lagrange function, right? So the in the Lagrange, in the minimax optimization, we get rid of the constraints over X. We only need to put non-negative constraints over the Lagrange multipliers, right? So following the same idea, it is very trivial to incorporate the equality constraints. So right now, we assume all your constraints are expressed by some inequalities, right? But you can use the same kind of idea to introduce Lagrange multipliers for equality constraints. So you can formulate the minimax optimization problem as well. So I will leave it as an exercise to help you deepen understanding this approach. So we focus on this primal form, right? But what is dual form, right? So dual form is just switching the position of min and max in the primal form. So in the primal form, the objective function is the Lagrange multiplier. In the inner level, we maximize the Lagrange function with respect to lambda, right? The multipliers. In the outer level, we minimize x, right? We first do maximization, then do the minimization. But in the dual form, we're going to first do the minimization over the Lagrange function. And in the outer level, we maximize the Lagrange function with non-negative multipliers. That's it. So dual form is simply to, to switch the order of min and max. This is called dual form. So now I want to ask, will the two types of formulation end up with the same optimal solution?
Could you repeat?
I mean, will the optimal function value for the dual form be the exact same as the optimal function value for the primal form? Give me a guess.
I think no.
Why?
I think we have to come up with one function that in two variables that if we first minimize and then maximize, we get another amount if we first maximize and then minimize. I think it's possible. I don't know. I have to think about that to find an example.
Okay. Any other suggestion or comments? Okay. Yeah, you have a great intuition. Yeah, you're right. So although they simply switch the min and max, the result can be very different. Actually, the optimal value of the dual form usually are different from the optimal value of the primal form. So in general, we can show that the dual is upper bounded by the primal. In other words, if you conduct max min over this Lagrange function, the optimal function value will be less than or equal to you conduct min-max optimization on this function. So this is just conclusion, just to give you a sense of the conclusion, and we won't go through the detailed proof. The proof is pretty simple. If you're interested in, they're all on slides. It's pretty straightforward, but just need you to be careful. They're not equivalent. In general, dual is worse than primal. And you can use two inequalities, combine them together to show that the optimal function value of the dual is less than or equal to the optimal function value of the primal. Okay, but there are always some exceptions, right? For support vector machines, we can show that dual form is equivalent to primal form, according to the so-called Slater's condition. And the reason is twofold. First, the objective is convex, the feasible region is convex. Second, this optimization satisfies the Slater's condition, namely the feasible region contains at least one interior point. You don't necessarily to know what is interior point, but you can imagine that what is interior point means that, okay, these all the points do not stay on the boundary. There is like at least one point stay inside the boundary, inside the feasible region rather than on the boundary. It's called Slater's condition. If you're doing convex optimization, if your feasible region contains at least one interior point, then there will be no duality gap. The dual form is equivalent to primal form. In other words, solving dual form is totally equivalent to solving the primal form. Okay? But those content is kind of core content in convex optimization. If you have taken this kind of course before, you should have learned that. But you haven't taken that course, that's fine, because we're not required to know the proof for that. Okay. Okay, now let us look at the SVM primal form, and then let us try to convert it into the dual form, like to solve the dual form and see what we can get. Right? So we'll focus on the soft SVM objective function, right? Because it is the most general form which can take care of the data which are even non-linearly separable, right? Non-linearly separable, not linearly separable. Right? So the soft SVM objective contains two terms, right? The first term is half of W transpose W, which corresponding to maximizing the margin, right? The second term is a summation over each instance, where each instance training example has a slack variable, right? CI. Of course, there's a trade-off between the regularization and this summation of slack variables. This is hyperparameter C, right? So what is slack variable? An idea? Why do we introduce slack variable?
To measure the distance between a data point and the margin and the hyperplane.
Yeah. Remember, in the original definition, we call it hard SVM. We require all the data points must stay on or outside margin, right? This is too aggressive requirement, right? You require the data is linearly separable, so all the data points must be on or outside the margin. Right? This is not feasible. What if the data points are not linearly separable, right? So to deal with that case, we allow a few examples to break into the margin, right? To stay inside margin, to intrude the margin. Right? We only find the max margin linear classifier for the remaining data points. How do we to actively choose which points can break into the margin, which points must be stay outside margin? We introduce this slack variable KCI, right? So we require for each instance, we have a slack variable KCI, which must be non-negative, and same time the function margin, this is function margin, product of the label and this prediction score must be no less than 1 minus the KCI, right? So when KCI is 0, what about xi? What about the position of xi?
It's on the margin.
Yeah, it stay on the margin or stay outside the margin, right?
Okay.
When KCI is absolutely bigger than 0, what will happen? When KCI is bigger than 0, say 0.5, then xi can intrude the margin, right? Can stay inside the margin. And why would we append the objective function by a summation of the slack variables? Can anyone recall? Yeah, try to memorize, try to recall what I have discussed before, right?
We ignore some data points that don't let us to find a linear classifier.
Can you repeat?
To ignore some points that don't let us to find the linear classifier.
Mm-hmm. Yeah, of course. That's why we introduced slack variables, right? But why should we add up all these KCI values in our objective function? We want to minimize the summation of the KCIs. Why?
To penalize them?
Yeah, right, to penalize them, right? Because we do not want many data points to break into the margin, right? We just want as few points to intrude the margin as possible. Why? Because the more data points you intrude the margin, break into the margin, the more likely you have a increased training error, right? Remember, your generalization error bound is determined by two terms. The first term is training error. The second term is determined by VC dimension, right? So you want to find a margin which is to be as large as possible. At the same time, you want to keep your training error to be as small as possible, right? Otherwise, overall, your generalization error will still be big. Right? That's why we add this summation of the slack variables to penalize the situation that too many points break into the margin. You want to as few points to break into the margin as possible. So yeah. So we should be clear. This is very important. We should be clear why this objective function is formulated in that way. What's the meaning for that? Okay. So now we can. This is a typical any question. All right. Okay. So this is a typical constraint optimization problem, right? So we have a convex objective function, which I mentioned before. This is a convex optimization problem, and for each particular training example, we have two constraints, right? So obviously, we can convert it into an equivalent minimax optimization problem on the Lagrange function, right? How can we do that? We can do it together, right? So first, this is a, let me switch to red pen. So this is our original objective function, right? This is ff. You can build it as f of x. So in our Lagrange function, we need to first copy the original objective function. Then for each constraint, we're going to introduce a Lagrange multiplier, right? So for each instance, we have two constraints. So for the constraint related to the function margin, we introduce alpha I. For the constraint of the non-negative slack variables, we introduce beta I, right? So then we just do the weighted summation of those constraints weighted by those Lagrange multipliers, add them into this objective function to construct our Lagrange form. Right? So the question is why in our Lagrange function we have a negative sign here. Why?
Because our constraints were negative in the Lagrange formulation, but here they are, for example, Ci is, epsilon I is non-negative.
Yes, exactly right. So we just follow the standard recipe. The standard recipe assumes that your objective function, each constraint is represented as something like that, right? A constraint function less than or equal to 0. So here we have it's bigger than or equal to, right? We need to switch the direction of the inequality, right? So that's why we should put a negative sign in front of it. But other than that, everything is the same, right? So this is objective function. So this part is the second type of constraints. So it's minus summation over each string example beta I Ci, right? And for here beta I Ci, and for the second summation is all about the constraints of the functional margins. Is also a summation over the training examples. We take negative sign to flip the inequality to be consistent with the general case, right? So you have a minus sign alpha I. You need to move this part to the left hand side. So it is function margin subtracted by 1 plus Ci. That's how we get the Lagrange function, right? So in the inner level, we maximize the Lagrange function with respect to non-negative multipliers. The multipliers are alpha i's and beta i's, right? In outer level, we minimize the Lagrange function with respect to the original variables, right? So in our soft SVM, we not only include the model parameters W and B, we also include the slack variables, because yeah, right? That's everything, right? So this is our primal form. Now, let us try to switch max and min to get a dual form. Right? So as I mentioned before, right? According to Slater's condition for convex optimization, we have the same solution. In other words, solving this dual form, namely this max-min problem, is equivalent to solving the primal form, min-max. So we're more interested in solving a max-min problem. As to why, we'll see later, right? So now let us look at this dual form, right? So dual form, this is our Lagrange function. In the dual form, we will first minimize the Lagrange function with respect to model parameters. And then we maximize the Lagrange function with respect to non-negative multipliers, right? So how to solve this problem? Just a very straightforward way. We just do it step by step, right? Let us just assume, excuse me? Any question? Okay, okay. So let us continue. So we can do it step by step. How can we do that? We can assume, okay, in the outer level, all those multipliers are given, are fixed, right? We're trying to solve the inner minimization with respect to WB and the slack variables, CIs, right? So how can we do that? We just take the gradient of the Lagrange function, set them to be 0, and see what can we get, right? This is pretty straightforward, right? So we have 3 types of parameters: the read vector, the bias parameter, and slack variables. So we take gradient with respect to the 3 types of variables. So we set the gradient of the Lagrange function with respect to W to be 0, with respect to the bias parameter to be 0, with respect to each slack variable to be 0. Right? And solving their gradient to be 0, end up with the 3 results. It is pretty straightforward, right? So we can take a look at the gradient with respect to W, right? So you have 2 terms containing W, right? So first term is the quadratic term. So the gradient of L with respect to W is simply W, right? Everyone has practiced this similar type of the vector gradient before, right? And for the second term, which is the summation, the outside is alpha I, yi, and W transpose xi. So it's linear to W, right? So when you take the gradient, you just leave the remaining part. This is alpha I, yi, and xi. And then if you set this gradient to be 0, you end up with W to be a weighted summation of all the input vectors. And each input vector is weighted by this Lagrange multiplier alpha I and the label yi. This is a very useful reformulation of the W. We'll talk about later. Right? And then we can take a look at the gradient of the L with respect to B to be 0, right? So there's only one term, including B, right? So if you take the gradient of the B, it's just put all the factors multiplying with B, right? So it's a summation over the training examples, alpha I, yi. You set the gradient to be 0, this weighted summation must be 0. And then we take the gradient with respect to each CI. So you have 3 terms contains CI, right? Just calculate gradient, you'll find, okay, set gradient to be 0, you'll see that, interestingly, you need to ensure that each alpha I and beta I, its summation must be the constant C. C is a hyperparameter which trade off the regularizar and the hinge loss, okay? So alpha I is the Lagrange multiplier for the constraint for, let me find it, constraint for the function margin, right? Beta I is a constraint for the KCI itself. Right? So when we solve the inner optimization problem in the dual form, we conclude that alpha I plus beta I must be C. And then we can substitute those results into the L, into the Lagrange form to see the result, right? So it turns out you will be able to greatly simplify the form of the Lagrange function. Right? So you can do it by yourself. It's really really straightforward. Just to do high school or junior school's maths, right? You end up with your objective function now is simplified in this form. You don't have like values which contain CIs. You don't have values which contains B, because there's when you apply this and apply this, they just disappear. And if you substitute this weighted summation of W for W in L, you end up with this quadratic summation. You have a minus half summation over I, summation over J. Each summand is Yi and Yg, alpha I, alpha J, in the product between Xi and Xg. Then plus the summation over the Lagrange multipliers alpha i's. But this can only be obtained when all of those three are satisfied. Meaning that if you want to simplify the inner minimization results into this objective, you have to include these two equalities, which are derived from here. Does it make sense?
Yes.
Any question? Is everybody comfortable? Okay. Okay, great. Yeah. If you have any question, just like in our normal class time, you just raise your voice and just ask. I would love to discuss with you, although I cannot see your face. Okay. So now we can further simplify this objective function, because we have solved the inner minimization problem. The only things left are the outer maximization problem, right? And we also add a few constraints, right? These constraints are derived from solving the inner minimization, right? So we see that, okay, in this simplified objective, right, we don't see any beta values. Beta values only appear in the constraints. We find that first, for each beta I, it must be alpha I plus beta I equals to C. In other words, beta I must be C minus alpha I. Right? Beta I is identified. Right? Beta I is 0, right? As long as we know alpha I. And also, we require beta I to be no less than 0, right? So that means as long as alpha I is less than or equal to C, we have a valid beta I, right? Because beta I is bigger than 0, and alpha I plus beta I must be C, right? In other words, we can get rid of beta I by simply adding a constraint of alpha I. As long as we have alpha I between 0 and C, we automatically have a valid beta I, because it is C minus alpha I, which is bigger than 0, no less than 0, right? So now we can, and further we can, you know, maximization is equivalent to minimization of the negative objective function, right? We can, for convenience, we can simply flip the sign of the objective. So we convert it into a minimization problem with respect to the constraint that each alpha I is between 0 and C, and also the summation of alpha I Yi's is 0. So this comes from this, right? And for the second constraint, because we have got rid of beta I, we can just throw it out. So now we have our final due form of the soft SVM. Any questions so far? Everyone is comfortable? Okay, great. Yeah, it looks much smoother than I thought. Okay, it's great. Okay, so this optimization is known to be the quadratic convex optimization. It's kind of standard form. For any convex optimization package, you have a routine to solve it. You actually do not necessarily need to develop your own algorithm to optimize it. You can call call the library to solve it by itself. Right? It's pretty standard. And the constraint is pretty simple as well, because it's just boundary constraints. Each Lagrange multiplier alpha I is between 0 and c, and also we have some linear constraint. That is, this linear combination must be 0, right? So, what's the benefit of this dual form? So, as we'll see, it will enable kernel trick and nonlinear classification. In other words, if you want to enable your support vector machines to do arbitrary nonlinear classification, you have to rely on this dual form. You have to solve this dual form. And also, it saves the model storage through the so-called support vectors. So what is support vectors? To see what is support vectors, we need to look at the solution of this dual form. Okay, so let us assume that we have solved this dual form, right? We call some powerful library from SciPy or from whatever convex optimization package. We have obtained the optimal Lagrange multipliers alpha 1 star to alpha n star. So the immediate question will be, how can we recover the optimal W and B from the optimal alpha 1 star to alpha n star, right? So here n is the number of training examples. Don't be confused here. Why? Because for each particular training example, we have a constraint. We have two constraints. One constraint for the select variable, the other constraints for the function margin. So for n training examples, we'll have n alpha 1, alpha i's, right? Okay. And then the question is, how can we obtain W and B from the optimal values alphas? Right? How can we do that? Any idea?
I think we have to go back to the reformulation, the first formulation, and then see what's the relation between alpha i's and W and B.
Right, right. Excellent. Very great answer, right? We need to trace back what we have, how we have derived to arrive at this dual form, right? So remember when we solve the inner minimization of the dual form, right? Namely, fix alpha and beta, those stuff, and we minimize the Lagrange function with respect to W and B and select variables. We have take the gradient of the Lagrange function with respect to W to be 0, right? When we solve it, remember we have this form, right? W equals to a weighted summation of the input vectors in the training set, and the weights are alpha I time multiplied with the label yi, right? So this holds for any solution, right? So that means if you have optimal values of alpha 1 star to alpha n star, you just replace those alpha i's with their optimal values, you got the optimal B vector W star. That's it. This one is pretty easy, right? So, but how do we get the bus parameter B? Right? The most complicated part is here. Right? It's not very easy to get B. Why? Even if you take a look at the gradient of the Lagrange function with respect to B, if you still remember, this is a summation of alpha I, yi, which is 0. Right? You have nothing term. There's no terms which contain B such that you can derive B in terms of whatever. B is just disappears, right? So how can we obtain B? To get B, we need to utilize the so-called KKT condition. So the KKT condition is kind of like the central part of the modern optimization, right? KKT condition has the convex version as convex version. Here we only introduce the convex version. So what is KKT condition? So KKT conditions are a set of test conditions for some particular optimization problem with respect to some input vector and some potential multipliers candidate. So here, I mean, it's multiplier candidates just means, okay, I want to test whether it is a valid multipliers, Lagrange multipliers. So let us introduce the detail. So what is KKT condition? So here we talk about the KKT conditions for a convex program. So in general, what is convex program? We minimize an objective function, which is convex, subject to big M constraints. Again, which is consistent with our general definition of constraint optimization. We assume each constraint is expressed as an inequality, f1x less than equal to 0, f2x less than equal to 0 until f big mx less than equal to 0. And all those constraint functions are convex. And also f0x are convex. This is called convex programming. And for arbitrary input x, which is x here, right? And also an m-dimensional lambda. So this m is consistent with the number of constraints here, right? So the KKT conditions, if x and lambda satisfy the KKT conditions for this particular convex program, that means they satisfy these 4 sets of conditions. The first set of condition is that x satisfies all the constraints. Namely, this particular x satisfies all this big M inequalities. This is reasonable, right? And secondly, this multipliers lambda is non-negative, meaning that every element of lambda is non-negative. And the third set of conditions is really interesting. This is our focus, right? So the third condition says that for every element in lambda and every corresponding constraint function, we have lambda m times fm of x equal to 0. So you can imagine if lambda is non-zero, then this constraint function must be 0. Meaning that x must stay on the boundary of the physical region, right? If fm of x is non-zero, meaning x is in the interior region, then the multiplier lambda must be 0. This is called complementary slackness. Very important for us to analyze the properties of the solutions. And the final condition is that the gradient of the Lagrange function evaluated at this particular x and lambda pair is 0. But again, although the gradient at x and lambda is 0, x and lambda are not local maximum or local minimum. It is a saddle point. Gradient 0 does not necessarily mean you reach local maximum, local minimum. It can be saddle point. Okay? So overall, KKT conditions is a set of test conditions for some type of optimization program. So here we're talking about convex program, right? So if for a particular pair of x and lambda, it satisfies all these 4 sets of conditions, we say, okay, the KKT